our discussion for today, catchy title page here, there are a lot of mosquitoes. Well, really not this time of year, too many, although maybe right now. In summertime here in Michigan, especially this summer, we had a lot of rain. And so all of a sudden we have this big population of mosquitoes, and then they go away. And by fall, we don't have any mosquitoes anymore. And so what we're talking about, the question is why? Or we can talk about something like, why aren't there any elephants living here in Michigan? Maybe you never thought about that. Why don't elephants live in America? Why is it that, and there may be a lot of reasons, and you're probably thinking, oh, there's some pretty good reasons. Maybe we hunt them, or maybe they just never lived here, or whatever, but why not? Or polar bears, or something like that. The talk about this is something called population ecology. Remember, a population is the number of organisms of a given species living in a given area. This means then that we are going to talk about how populations work. How populations work. So we've already had this definition. We talked about this definition a while ago in our introductory ecology PowerPoint. You can refer back to that if you want. The number of organisms of a given species living in a given area. If we look at, let's talk about mosquitoes. If we look at mosquitoes, for instance, okay, we can make a graph of a population of mosquitoes, something like this. At the bottom of the x-axis here is time. Y-axis would be number of mosquitoes. And it's not quite accurate because, as we'll see, and we'll do some stuff with this in class, but this could be winter. And then in the spring we get some mosquitoes, we get a good rain, it warms up, boom, we get this huge growth of mosquitoes. And then the mosquito population kind of levels off, and what eventually happens, it does that again. No, it doesn't always happen with populations of certain things. And we'll see why this part happens in a minute. We can talk about two different parts of this graph. The part of the graph where the population grows really fast is called exponential growth. Remember, an exponent would be something like x squared or x cubed, where if you cube a number, a square number, that number gets bigger very fast. Okay, the definition of exponential growth is extremely rapid growth, with the birth rate much higher than the death rate. The second part of the graph is something called carrying capacity. This line here, this level line, although in real populations, as we'll see, it's not necessarily level, could go up and down around a number, specific number of organisms. That's called the carrying capacity. The carrying capacity is the population an ecosystem can actually support. How many organisms could actually live there? And when you get there, the birth rate and death rate are nearly equal. Some years the death rate is higher than the birth rate, the population drops. Some years the birth rate is higher than the death rate, and the population rises. Okay, so why? Well, let me give you the definition here in a second. Limiting factors. Things that limit a population's growth and keep it at a carrying capacity. In other words, what defines this number? What defines that number? Why did the white-tailed deer population stop growing? Why is the polar bear population 0 here in Michigan? Why did the mosquito population explode and then shrink back? Okay? So we're going to talk about what drives a population's growth, essentially. And to do that, we're going to talk about two kinds of limiting factors. The first kind of limiting factor is something called a density-dependent factor. A density-dependent factor. And in order to know what that means, I think everybody knows what the word depend means, to need something to happen. So this is referring to population density. Population density. Okay, and I'm going to talk about population density here in a second. But the definition of density-dependent factors are things that affect large, crowded populations. Things that affect large, crowded populations. Quick examples. Two, we're going to talk about human population here because it's just the easiest for us to measure. This is a country called China. Maybe you've heard of it. One in every 6 people in the world live in China. The reason we're talking about China is China has some of the most population dense areas in the world. What do we mean by population density? Population, sorry about that. Density would be the number of things per area. Right down here, off the coast of China, right there, is an island called Macau. The island of Macau is less than 1 square mile. Less than 1 square mile. Just so you know, a square mile out here in the country would be the area from Cleveland to Roosevelt between 48th Street and East Street. Okay? So a square mile. So that island is smaller than a square mile. Macau has 48,000 people per square mile. 48,000 people per square mile. And maybe you're wondering if that's a lot. Well, the population density of the city of Coopersville, that means the defined boundaries of Coopersville, is 800 people per square mile. Coopersville is about 5 square miles and about 4,000 people live in it. About. I think it may be a little bit more than that. So, Macau, I'm going to try to do the math here a second. 480 divided by 8. 8 goes into... Macau is about 50 times more people, 500 times more people than we do. Okay, number 1, competition. Competition. What is competition? Well, remember now, we're talking about things that limit a population. Competition would be fighting for something. There are 4 major things that living things compete for. And some of you, here's my boxing penguin. Some of you might be thinking of like fighting for a mate. Well, that's different kind of competition. That doesn't really affect you, the population, necessarily, because something's going to mate with something else. Living things compete for food, space, light, and water. Animals, the A stands for animal, the P stands for plant. Animals compete for food. And that you probably can just think about that and you understand that they fight over food. Plants and animals compete for space. Why do plants spread their branches out? To occupy more space so they can get more light. Animals compete for a place to live or a habitat. Plants, already mentioned, compete for light, and both plants and animals compete for water. Plants by putting down roots and spreading them out. Animals by, well, you can think about that, competing for water. That's the first kind of density-dependent factor. Here's the second, predation. We're going to talk about predation later, okay? But here's a lynx and a hare. The lynx chases the hare. Lynx catches the hare and eats it. That's predator-prey relationship. The more hares, the more lynxes, and vice versa. We'll spend more time with this in class. Letter C, stress/disease. The more closely grouped the population, there's increased disease. Now let's think about this. When are you most often sick? You are not most often sick in the summertime. You are most often sick during school. Maybe you never thought about that. And a lot of people then say, well, it's because it's cold outside. Really? I beg to differ. You get sick because you're in a closely grouped population. You're sitting in class every day with 30 other people. You are closer to 29 people you aren't related to every day than you are all summer long. I bet all summer long, except maybe at church, one time a week for an hour, you are close to a bunch of other people. Otherwise, you're pretty much spread out. And even at church, it's a bigger room. There's a lot more places for viruses and bacteria to go. So the more closely grouped populations, you have an increased stress level, which serves to increase disease, and it's easier to transmit diseases. So, of course, disease increases death rate. Letter D, parasites. We're going to talk about parasites in a later lecture. It's symbiosis. Parasites are kind of like predators, except they don't really want to kill their host. Okay? So a parasite, like a flea or a tapeworm, the more rabbits there are around, the more fleas. The more dogs there are around, the more fleas. And there are more hosts. Okay? Parasites lower birth rate because they take away energy. Now you're thinking fleas? Not really, not necessarily. Okay? Not necessarily a flea on a dog, but something like a tapeworm, okay, or a mosquito that actually gives you a disease like malaria, those could really lower birth rate. They usually don't increase death rate, although in some cases, some parasites do kill their host. Number 2, density-independent limiting factors. Things that limit a population regardless of numbers. Doesn't matter how many there are. Doesn't matter if there's one rabbit living in this woods on the picture or a million. That one rabbit will be soon cooked rabbit, and the million rabbits would soon be cooked rabbits. That would limit the population of rabbits. Here are some examples: weather, fires, climate, floods, blizzards. All these things are density-independent limiting factors. Why don't mosquitoes live here in the winter? Well, it's too cold. They don't survive. They're insects. They don't make it through the winter unless they have somewhere warm to be. So we don't have mosquitoes here in Michigan in the winter. We don't have polar bears in Michigan. We don't have elephants in Michigan. There could be other factors about that, but probably not. Probably not. The polar bears, you can probably think right away, well, they're adapted to a very cold environment. Control their population, no matter how many there are here. Density-independent limiting factors.